Okay, thank you very much. My name is Melissa. I will try to present you the modeling, analysis, design, as well as the detailing of the reinforcement bars of underground water tank using Etabs 2016. Now let's open the program. Now the program is opening. It is taking some time. Good. Now the program is open. Now let me click new model because I wanted to model a new underground water tank. So click new model. Okay, the model initialization dialog box is coming. Now click use built-in setting. Here, now the model initialization has been set to Eurocode standard. That is per unit is metric SI. Still section database is Eurocode because I am using Eurocode. The still design code is Eurocode 3 2005, but for the time being I'll not be using this because all the structure of underground water tanks are going to be constructed using concrete and reinforcement bar and the concrete design code, that is Eurocode 2 2004. Now primarily I will be using this concrete design code, this one. Now click OK. Here the new model cube template is coming. Here let's try to define the grid line. Now to define the grid line first, let me show you the sketch of the underground water tank, what it looks like. Now to see the plan of the underground water tank, to see the plan view. Here there is a compartment wall at the midway of the longest wall. Here the total length of the underground water tank is 12 meters. And now the width of the underground water tank is 6 meters. So the number of grid on x direction is 3. The number of grid on y direction is 2. So let's define the size of the underground water tank using the grid system. Here I have 3 grid lines, and here I have 2 grid lines. Now the spacing of grid line in x direction, it is 6 meters. The spacing of grids in y directions, it is 6 meters. Now the distance between grids is 6 meters. Now let's come to the story dimension data. Here the bottom story height is 4.2 meters. The typical story height is similarly 4.2 meters. The number of stories is 1 because I have 1 story for the underground water tank. Now here, if you wanted to edit the grid system, you can use this option. Now edit grid data. You can edit all the grid system. If you wanted to change the dimension from 6 to 8, you can make this 8. You can use the display grid data system 6 the distance between grids, and you can add also the grid ID here. So Now grid only. Click OK. Okay, now the green lines defining the size of the underground water tank is coming. So here we have two windows. One is showing the 3D and the other is showing the plan of the underground water tank. Now the first step is finishing all the tasks that are going to be performed in the define menu. And the second one is now after completing all the tasks of the define menu, just we'll go to the draw menu. And then after finishing all the draw menu, we will go to the assign menu. And finishing all the assign menu, we will go to the analyze menu. And after that, finishing the analyze menu, we will go to the design menu. And finishing all the tasks associated with the design menu, we will come back to the display menu to see all the results. And the display menu and the detailing menu will be worked simultaneously. So now let's start at the define menu. Now let's define the material property. Add new material. Here, add new material property dialog box is coming. Here, we have to select the Europe because I'm going to use Eurocode. Here, the material type, select concrete. Now, here, there are lists of the concrete grades that are going to be developed using Eurocode. Here, I can use C3037 because the underground water tank is a water structure. So I have to use higher grades of concrete. So now click OK. Here, this C30 forward SR37 is scanning. Now, this material property data describes the properties of C37 concrete grades. Now, this isotropic. Here, all those parameters should not be changed. You have to use as it is. It is not advisable to change those default parameters. And now, to modify show material property design data. Here, this is 27. Now, be careful here. Characteristic concrete cylinder strength FCK it is 27.58. Here, this material name indicated that the characteristic concrete cylinder strength FCK value it is 30 megapascal. So you have to make it 30. So this value must be similar to the value of the number coming before the forward slash. Now click OK. Here, the material characteristic concrete cylinder strength is 30. Now click OK. Okay, now add the second material that will be used for the design of the underground water tank, which is the reinforcement bar, that means the rebar. Here, Eurocode doesn't have a standard, a default standard associated with the European standard. Now click OK. Here, the new dialog box is coming. Now, I'm going to use the 500 megapascal reinforcement bar steel grade. Here, all those parameters are coming by default. Don't change all those parameters. So you have to take it as it is. It is not advisable to change the parameter. So go to the modify data. So now, as I'm going to use the rebar 500 grade, so I have to make it 500 megapascal of the yield strength. And similarly, I have to uh, fill this 500 megapascal for expected yield strength. So when we come to the minimum tensile strength, now the minimum tensile strength is the value of the yield strength multiplied by the sum factor. This factor is coming from the value of the elongation. If the elongation is 8%, so we need to multiply the yield strength by 1.08. If the elongation of the reinforcement bar is 12, so we need to multiply the yield strength by a value of 1.12. So the tensile strength depends on the elongation of the reinforcement bar. The elongation of the reinforcement bar in turn depends on also the ductility class of the reinforcement bar. So for the time being, we need to multiply 500 by 1.08. Now I'm considering that the elongation of the reinforcement bar grade is 8%. So similarly, the expected tensile strength is 540. Now click OK. Click OK. Now I have finished defining of the reinforcement bar as well as the concrete grades. Now the second one is define the section property. Here we have two section property, the slab section as well as the wall section. Now let me define the slab section first. Here we have two slabs, the top slab and the base slab. Now the underground, the base slab will be used later for the design of the foundation, but I'm going to use the superstructure for the modeling of this underground water tank. Now select C3037 here. Now select the slab. Now be careful here when you select the modeling tab, you have to select the shielding. If you select the membrane, so the membrane doesn't have any bending strength. So if you use the membrane modeling type for the cover slab, later the deflection will be too much. That means it will be in kilometer, which is unrealistic. So use the membrane modeling type for the roof cover, not for the roof slab. And also similarly, don't use the Celtic. The Celtic modeling type is used for the foundation slab, that is the mat slab, the isolated footing. Don't use for the thinner slab. So the modeling type will the Celtic. Now here use 200 millimeter thickness of the cover slab. Now if the deflection requirement or the serviceability requirement is not satisfied or fulfilled, so we need to revise this Tekla later. So click OK. Now add now click OK. So define the second cross section, which is the wall cross section. Now here add the new material, the new property, that is 300. So here the modeling type is specified. The wall material is concrete. Now you have to use the shading, and the thickness is 300 millimeter. So click OK. Now click OK. I have finished defining of all the wall and the cover slabs of the underground water tank. Secondly, here there is a spring property parameter. Now I will not be using this for the modeling and designing of the superstructure of the underground water tank. Later, I will be using the spring property parameter, especially the area spring file designing of the underground water tank space slab. So for the time being, I will omit this one. Now, let me go to the diaphragm. Here, try to check the diaphragm type. You have to use the rigid diaphragm. So click OK. Now click OK. Now, let's go to also the pier level. So as I'm going to model the shear wall, so every segment of the shear wall should be assigned with different types of pier level. So I have 5 segments of the shear wall. So we need to have 5 piers. So it is 4, it is 5. Okay, now go to the, I don't have any spandrel lever, so no need of using group definition, no need of using section cut. So let me go to the load pattern. Here, by default, the dead load and the live load is considered. Here now, I will add another load type, that is the water pressure. Here, the behavior or the nature of water pressure is similar to the live load, as the level to water pressure load is variable. At some time it may be full of the tank, and at some time it may be semi-full, and at some time it will be empty. So it will be considered as a variable load. The second one is the soil pressure. The behavior of soil pressure is like a supported load. So now add new load. And later the water gravity load. But for this case I will not be using it. The water gravity load. This load will be used for the design of the base slab. And this behavior is the live load. So totally I will have 5 load type, but mainly I will be using those 4 loads. Now click OK. Now go to the load case type. Here, now the direction of the local axis must be adjusted in such a way that there will be a consistent application of the direction of the load. Now, here, if I have the plan of the, if this is the, plan of the underground water tank. So, the water pressure will be acting in this direction, and in this direction, and in this direction, and in this direction. So the local z-axis should be in this direction or in this direction. It must have the same direction in order to visualize the deformation of the structures. So to make this consistent, the direction of the soil pressure is in opposite direction of the water pressure. So we have to make the factor of the water pressure -1, because the water pressure is acting in the negative z direction. So I have to adjust the local z in this way. If this one is also in this way, this one is in this way, this one is also in this way, to the inside zone of the underground water tank. So here the water pressure, go to the water pressure. Now here it is -1. So all the load applied, all the water pressure applied to the underground water tank will be multiplied by -1. Now the sign will be reversed. Now click OK. Now just click OK. So here, let me go to also load combinations. Now add the default load combination. Here I am going to design the slab as well as the wall. So I have to click all those. Now here click convert to user combination editable because later I may be using the editing option. So here there are two for the wall and two for the slab. Here totally two load combinations for slab and two load combination for walls are developed. Now add new combo. Sorry. Here now there are also other combinations. Now here this is the underground water tank. Look, there are three options or three scenario. The first scenario is the first option is there will be also underground water tank inside the tank. Here the tank will be full of water while there is no backfill. This phenomena will occur during the leakage test of the underground water tank. After the completion of the construction, we will not backfill the soil, so it will be laid vacant for the inspection of leakage. So in this case, the dead load, the live load, and the water pressure will be acting. And the second option will be, after the completion of the constructions and after the finishing of the leakage test, the soil will be replaced to its original position. Now we will have all the load. So the load plus the live load plus the water pressure plus the soil pressure. Look it. The third one is by default. This one is included in the default design load combination. And the third one is what the if there is no water inside the tank. If there is no water inside the tank, that is, it may be at the time of maintenance. So in this case, dead load plus the live load. I will not have and plus the water pressure here, the soil pressure. At the time of maintenance, or just in order to maintaining the inside part, or in order to treat or clean the inside parts of the underground water tank. All those three options will be applied for serviceability limit state as well as ultimate limit state, and for the combination of the load this is considered, but this and this are not considered. So now let's go to the combo one, that is the load. Add first. Now let me find the serviceability. The live load, add the water pressure, add the soil pressure at the water gravity. If there is water gravity for the design of at, this is for combo surface of all loads. So now add a copy of this one. Add a copy of this one. The dead load, the live load, and the water pressure. Done. So here, excluding this one. This is the actual soil pressure. Now here, the okay. Now add copy of combo this one also. Now the load and the live load, because I will not be have water pressure. So here, add copy of combo for serviceability, for alternate. You see that the load is 1.35 and the live load is 1.5. The water pressure is 1.5. The soil pressure is 1.35 and the water gravity is 1.5. Now I have finished the defining of the combo ultimate all loads. That's okay. And here add copy of combo. Now this one is an ultimate. Now here the dead load is 1.35 and now the live load is 1.5. The water pressure is 1.5 and the water gravity load is 1.5. Now click OK. Sorry. Now click OK. Here now the ultimate this one. Okay, now let's modify this one. Ultimate. Ultimate. Now to copy of this one. Ultimate here. It is 1.35. Now the live load is 1.5. and the water pressure it is 1.5, and the water gravity it is 1.5. Sorry, I have to find it before. So now let me show you ultimate. Now this is the service. Ultimate. Now the service. Now let me check it. Hard copy of this one. Yes. And this is ultimate. Here it is 1.35. And here it is 1.5. This is now ultimate. Ultimate 2. Okay, now perfect. Now here I have finished the defining all the tasks of the define menu. Now let me go to the draw menu. Here, just let me draw the shore. Select the wall 300. Okay, now let me draw the slab, the cover slab. Okay, now define the base support. Go to the assignment, joint, restrain. Select the fixer support. Here's the fixer supports are assigned to the base of the wall. Okay, here we have finished defining of all the slab, the shear, and the supports of the uh, at the base supports of the shear wall, and all the cross section associated with the shear wall as well as the cover slab. Now let me show you how to assign the mesh to the slab as well as to the wall of the underground water tank. Here, to do this, just first, now select the slab section. Select the top slab. Click select. Here, the top slab is selected. One shell selected. Now go to the assignment. Here, shell for automation option. Then here, let me click this AutoCAD. Select this one. It is 1 millimeter. Apply. Okay. Second, now let me apply the mesh to the wall. To do this, go to select, property. Now select the wall section. Now the wall section is selected. 5 shells are selected. Now go to the assignment. Now here, now wall automation option. Here now, select the auto rectangular mesh because the walls are rectangular. Just go to the advanced setting. Now make it 1 meter. 1 meter by 1 meter mesh will be applied to the wall. Now click OK. Now apply. So to view the meshes of the slab and the wall. So go to the display option, and here try to shell analysis mesh. So click this one, now apply. So apply to all the windows. Now look at the mesh of the walls as well as the slab is clearly seen in the 3D. Okay, now we have assigned the mesh to the wall and to the cover slab. And now let's assign the diaphragm to the cover slab. To do this, first we need to select the slab. Just click here in order to select the slab. One shear is selected. Then go to assign menu. Here, diaphragm. Now select, apply. Okay. Here, now the diaphragm is applied to the cover slab, and it is located at the centroid of the cover slab. The centroid of the cover slab is the center of mass of the cover slab, or the center of gravity location of the cover slab. So now I have finished assigning of the mesh and the diaphragm. Next, I will show you how to assign the pier to the walls of the underground water tank. Now to do this, let's go to for simplicity. Now select the cover slab and make it hide. Have selected object. So try to select this wall and assign the pier level. So pier 1 for this one, and pier 2 for this one, and pier 3 for this one, pier 4 for this one, and finally pier 5 for the compartment one. Now here all the pier levels are displayed on the wall. Now second, now let me apply the loads. To do this, now click show all objects. Now select the slab because I want to apply the live load on the cover slab. Now to do this, go to the assign menu, and here the shell load. Now the uniform load. Here select the live load. Now the approximate volume of 2 kilonewton per meter square of live load will be applied on the cover slab. So click apply. Here the value of the live load is displayed over the slab. Now click OK. So select this slab. Now you hide the selected objects in order to select easily the walls. So here we need to apply the swell pressure and the water pressure on the wall. Now to do this, now let me clearly define the application of the load of water and soil. Here we will have two options where critical lateral pressure acts on the wall. Now option 1. After the completion of the construction of the water tank, there will be a leakage test. To do the leakage test, we should not return back the backfill material, so we make vacant the periphery of the underground water tank walls. So during this time, there will no a backfill soil Hence, there will be only lateral water pressure acting on the wall. So, here, to do this, we need to use ranking coefficient, so Ranking's factor, in order to multiply the value of the soil pressure. But for in this case, the ranking coefficient is 0 in the case of the determination of the water pressure. But in the case of soil pressure, we need to use it. So here, now, let me clarify how the water pressure is going to be calculated. Now, considering that this is the tank, this is, the freeboard. Here, the water pressure will be applied like this. This is the water pressure. Now, this is the maximum water pressure. And this is also the minimum water pressure, which is 0. But here, this maximum water pressure will be calculated the gamma of water times the height of the water. So now, this is the base of the wall, and this is the direction of Z. Now, here, the Pmax in essence, the pressure which is acting at the base of the slab. Now, Pmax, which is equal to gamma water, that is the unit weight of the water times the height of the water, which equals to 9.81 times 3.7. Now 3.7 is the height of the water. Here this one is T3.7. Now considering the freeboard, this freeboard is 30 centimeter, and the total height of the shear wall is 4.2, meaning from the center of the bottom slab to the center of the cover slab. But now, here, that means during the modeling, this is the center of the cover slab, and this is the center of the bottom slab. Here, this is the numerical model, the analytical model. Now, the height of the wall is 4.2. This is in the case of analytical model, but in the case of physical model, the total height of the wall is this one. Anyway, 4.2 meter will be taken. So in the case of soil pressure, I will not be using in the case of water pressure, but in the case of water pressure, it's 3.7 is enough. Here, this value will be 36.3 kilonewton per meter square. Now here, the minimum, this is the maximum water pressure at this point. The minimum water pressure will be 0. That means at the top or at the top of the wall. Now, as I will be selecting the total height of the wall while I'm going to apply the water pressure. So, however, the water is below the freeboard, so I will be the difference is insignificant, or just to be safe. So this will not be that much different. So now here the Pmin, which is equal to 0 at this point, that is water pressure will be 0 at this point, will be maximum or 36.3 at this point. So considering all those two values, here I have the pressure formula. P equals to Ax plus By plus Z plus D. Now the pressure is acting along the Z direction, so this value and this value will be 0. Now what will be left? P is equal to CZ plus D. Now here at C is equal to 0, then P equal to 36.3. That means at Z equals to 0, P equals T. That means P equals to 36.3. And now substituting D 36.3 in the above equation, so we will get C equal to minus 9.73 kilonewton per meter cube. So now the parameter D and DC are calculated. Now let me replace. Sorry. Okay, sorry. Now let me apply. Okay, close this one. Yes. Okay, sorry. Okay. Now to this. Now select all the loads. Now select the exterior parts of the wall. Don't select the compartment because the water pressure acting in this direction can be counterbalanced to water pressure acting in this direction, so the net effect is 0. So now go to the assignment, the shell load, non-uniform load. Now here in this non-uniform load dialog box, now select the water pressure because I am going to apply the water pressure. Here, be sure that look at 3 axis is selected. That means the direction where the water pressure is acting. Now paste here 9.73, the value of C. Now here apply. Here the water pressure is applied on the wall. Now we have to see all the values provided here will be displayed here. Look. Now let me select also the swell pressure. It shows that the local axis is selected. Now let's go to the swell pressure. Here the option 2. After a completion of the construction of the water tank, there will be maintenance. To do this, the water will be empty. So there will be a full of backfill soil and surcharge load at the surface of the backfill. Hence, there will be only lateral soil pressure acting on the wall. As the tank is free from water, there is no water pressure in the tank during the maintenance time. So, to calculate the soil pressure acting on the underground water tank, we need to use a ranking coefficient. Let's calculate the maximum soil pressure at the base of the wall due to the backfill. Here, now let me review how the soil pressure is calculated. Here, this is the underground water tank. Now, here there is a surcharge load, that is Q, which is nearly equals to 12 kilonewton per meter cube. This is the surcharge load. Surcharge load is the load occur due to the vehicles or due to the construction materials which is dumped over the surface of the backfill. Here, this is the backfill material. Now the backfill material induces the lateral soil pressure. Here, this is, the P1, and here this surcharge load will be superimposed into rectangular lateral load, this one, which is, this load is P2. So here at the base of the slab we have two loads. The first one is P1 and the second load is P2. So at the base of the wall, the maximum pressure will be P1 plus P2. So P1 is the swell pressure, and P2 is the swell pressure, which is due to the the surcharge load. So this those pressures can be calculated like this: P1 max, this P1 max, which is equal to the ranking active earth pressure times gamma of soil times the height of the soil. Here the height of the soil is 4.2, which is to the full height of the shore. Now the ranking coefficient, the active ranking coefficient, will be equal to 1 minus sine theta divided by 1 plus sine theta multiplied by 20 kilonewton per meter cube times 4.2 meter. This gives us 27.72. This is the maximum lateral soil pressure due to the backfill material. Let us also calculate the maximum soil pressure due to the surcharge load. Here the surcharge load will be superimposed into the rectangular lateral soil pressure. Now this is P2 max, which is equal to the ranking coefficient at rest condition, that is K0, times the surcharge load, which is the ranking coefficient at rest condition, will be 1 minus sine theta, which is times, it is 12, the surcharge load. So this gives us 60 kilonewton per meter square. Here the P total can be calculated as P1 plus P2. That means this load, this pressure plus this pressure, which is 33.72. Now taking all this total pressure, which is 33.72, now substitute this pressure in the place of P. Here we have the pressure formula, as the pressure is acting on the vertical directions, that means along the Z direction, so we will not have the value X and Y. Sorry. Now P equals to CZ plus T. So P equals to, that means this value will be 0, CZ plus T. P is equal to CZ plus T. Now at Z equals to 0, that means at this point, at the base of the wall, then P equals to 33.72. Using the above pressure equation, this equation, we can find the value of T. So the value of T becomes 33.72. Now substitute the value of D in this formula. At the height of 4.2, then the pressure will be minus 8.03 kilonewton per meter cube. Now the value of C and D are calculated in the case of soil pressure. So now let me copy this value and replace this into this value. So here minus 8.03 minus 8.03. Now here be sure that the soil pressure is selected, and now be sure that the local axis is selected. Now click up. Here I didn't select the walls, so select all the walls. Now apply. Here. Now the soil pressure that I have applied is displayed here. Now look, both the soil pressure and the water pressure values are displayed. It's good, perfect. Now come to here. The soil pressure and the water pressures value are displayed. Perfect. Now just come to here also. The soil pressure and the water pressure values are displayed here. Now good. Now come to here also. Check. Now the soil pressure and the water pressure values are applied here. Now all the loads are correctly applied to the wall as well as to the slab. Now secondly, here we have finished the application of all the load. So here now let's run the analysis to observe the deflections of the cover slab as well as the water tank's wall. Now to do this, now click run analysis. So now let me tank recent 2. Save. Now Etabs is calculating and analyzing the underground water tank based on the provided soil pressure, water pressures, live loads, and all the parameters. Here, now let me show all objects because previously I have hidden the cover slab. Now let me observe the deflections of the water, the deflection of the structure due to the water pressure. Here, now select Z direction. Now apply. Sorry. Here, now the deflections of the underground water tank due to the water pressure looks like this one. So the water pressure will be acting from the inside to outside of the tank, while the soil pressure is acting from outside to the inside of the tank. So the deflection shape of the underground water tank will be to the inside of to the direction of the tank in the case of soil pressure, and in the case of water pressure the reverse one. Now let me show you the animations. Here the animation, this is the animation of the underground water tank while the water pressure is acting on the wall. Now if you click stop animation, now the underground water tank wall will be bulging out. That means the water pressure is acting outside of the tank. So in this case, the shear wall will be deflected outward of the tank. So here, check all the walls are deflected outward. Look. So the outward deflection of the shear wall shows that our model is perfect. Now here the simulation of the deflection of the underground water tank is similar to the realistic deflection behavior of the underground water tank due to the water pressure. Now let me show you also the deflection of the underground water tank due to the soil pressure, which is the opposite of the water pressure. Here to do this, now go to the deformed shape dialog box and select the soil pressure. Now apply. Here it is in opposite directions. Now it bulges toward this tank. Now it deflects toward the tank because the swell pressure is acting in this direction, in this direction, in this direction, and in this direction. No, it deflected toward the tank. Now let me show you the animation. How the simulation of the underground water tank looks like. Here. Now the soil is acting in this direction, so it deflects towards the tank. And if we apply the soil pressure in this direction, it deflects towards the tank, like this, like this. And now stop the animation. Here, the deflection is towards the tank. Now observe all the sides of the wall. Here, it deflects towards the tank. Now also see here, it deflects towards the tank. This shows that the simulation of the underground water tank due to the soil pressure is similar to the realistic deformation behavior of the underground water tank. So now this shows that our model is perfect. Here, now let me show you also the maximum deflection of the wall as well as the cover slab. And later we will compare the allowable deflection limits provided by the Eurocode. To do this, now go to the combo. Here we have set 3 options for serviceability limit tests. The first one is, this one, this one, this one. Let me test the first one is apply. In this case, we have a deformation of 0.79. Here 0.79 means here at this point, use it 0.791. Here at the center of the cover slab. And now, in the second option, here when all the loads are applied simultaneously, here it is 0.96, meaning approximately it is 1 millimeter deflection downward. And here, this is also minus 0.813 millimeter downward. Here, it is indicated here. So, the maximum deflection will occur when all the loads are acting simultaneously, that is option 2. Now, nearly equals to 0.96, which is 2 millimeter. Here, the Eurocode recommends the maximum deflection of the beam or the slab should not be greater than 250, but in our case it is 2 millimeter. But in this case it is L over 250 will be it is 6 meter divided by 250, which is equal to times 1000. So it is 24 millimeter. So 2 millimeter is too much less than 24 millimeter. So this concludes that our deflection is under the allowable limit. So it is okay. Okay, now sorry. Okay. Now we have already checked the deflections due to the soil pressure, the water pressure, and the gravity load. So we have got a maximum deflection of the slab 2 mm, which is much lower than the allowable deflection, which is recommended by Eurocode. That means the L over 250, which is 24 mm. Okay, next I will show you how to design the wall. Okay, I will show first the design of the cover slab. To do this, now click on deformation, and now let me come to the plan view, and here select the cover slab, and just go to the edit menu. Now to assign the strips to the cover slab. Now here I have story 1. Now select the story 1. Include the middle strips. Now first let me define the strips along X direction. Now click OK. Now click Apply. Here the middle strips as well as the column strips are drawn. And now let me draw also strips along the Y direction. Now click Apply. Here all the middle strips and the column strips are drawn. So now run the analysis. Now Etabs is analyzing the cover slab. Here, now let me design the cover slab. Now first to do this, first select the cover slab. So here go to the now select the design combination. Now by default, Eurocode select us to design combination for slab. So here go to the reverse selection rules in order to fix the minimum and the maximum diameter of the slab. Here the minimum is 10, the maximum is 12 is enough. Now the minimum is 10 and the maximum is 12 is enough. And similarly, now click OK. Now check Eurocode is selected here. OK. Now click designing of the slab. Here the middle strips and the column strips are designed. Now to view the flexure design. Now import the minimum reinforcement bar. Now apply. Here the minimum reinforcement bar is applied. Now click OK. So now go to the display flexure design, and now in strip PP, that means along Y direction, that is applied. Now click OK. Here the reinforcement bar at the middle strips as well as at the column strips for the Y directions are drawn here. Now the maximum reinforcement area is displayed 364 for the middle strips, and similarly for the column strips is also 264. I mean it is 345 for the column strips. Sorry, for the column strips 364. This is for the column strips, and 364 is for the middle the column strips, and for the middle strips it is 364, which is the same as the reinforcement area along the X direction. Now display. Now let me check once also along x direction. It is 364. So if you put 364 here, now the the area of the reinforcement bar is 364 millimeters square per meter width of the slab at the middle strips and at the column strips. So this indicates that we have to use 8 millimeter diameter reinforcement bar at spacing of 275 millimeter at the bottom faces of the middle strips and at the top faces of the column strips. So this is all about the slab design. Now let me design also the wall. Now to do this we have to select all the color. So select this one, select this one. Now first we have to hide the cover slab. So to select all the wall section. Sorry. Select a property wall section. Over here 5 walls are selected. Now okay. Now 5 walls are selected. So here go to the shear menu. Now view reference. Now Eurocode has to be selected. Okay. Now go to the shear wall also. Leave a selection rule. So here the smallest diameter of the wall must be 10 and it has to be also 12. And when we come to here 10, it is 12. Now here also it is 10 and here it is 12. Now click OK. So just come to also the define general peer section, assign peer. Also now peer override. Here 10, 10, 250 is selected. Now I have to try for this cross section and for this spacing. If it is okay, we'll continue. If it is not okay, we will revise it again. So now click. So run analysis. Now Etabs is analyzing the shear walls based on the provided data. So here analysis is complete and now let's come to the design of the shear wall. Here now the reinforcement bar, the area of the reinforcement bar is displayed on the wall. Now here do this. Now click on this surface to view the area of the reinforcement area with respect to the minimum required reinforcement ratio. Here the minimum required reinforcement ratio should be less than the current reinforcement ratio. So here in this case it is a little bit lower than the minimum reinforcement ratio, or so we need to reduce the spacing of the reinforcement bar in order to increase, in order to make the ratio a little bit higher than the minimum reinforcement ratio. So to do this, just go to the override menu. So here we need to reduce, that is 220. Now click OK. So now see this 24, this 24, it is a little bit also higher. Just again, so make it this 200. 200. Now OK. Here, it is 28, perfect. Now, the current reinforcement ratio a little bit higher than the required reinforcement ratio. That means the provision of the amount of reinforcement area is a little bit economic. So, here, we need to provide 10 millimeter diameter reinforcement bar at a spacing of 200 millimeter for all the walls as a main reinforcement bar. So now go to the select menu, hit previous selection. Now select property wall, all 300 select. Now all the shear walls are selected. Just go to the shear wall design. So now revise peer override. Here make it 200. Now okay. Now here design the shear wall. Etabs is designing the shear wall. Here now the shear wall is designed as per the provided reinforcements bar and spacing. Now it is perfect. Now our design is completed. So this is all about the modeling, designing, the modeling, the analyzing, the designing, as well as the detailing of the reinforcement bar of the underground water tank using Etabs 2016. I hope you have got very important information on the modeling, the analyzing, the designing, as well as the detailing of the underground water tank, walls, and slabs. This is all about this tutorial. Next times I will be show you how to model and design the underground water tanks base slab, and similarly how to also design and detail the circular water tank using TAP 2016. Thank you very much. Bye bye.